Hello fellow skeptics, I'm Luther Name, and this is the 15th video in a series that asks the question, is something wrong with modern physics? If so, what? And can it be fixed? Now, in preparing for this video, I went back and reviewed my prior ones, which is what I typically do for ensuring that there's continuity and clarity in all the points I want to make. I found that it was probably worthwhile putting a review together that basically summarized what I covered in the prior two videos on the Doppler and the aberration effects, both of which were described in Einstein's seminal work on special relativity in his 1905 paper. Now, what I've done is in this video, basically I put together a more extensive set of visual representations covering the same topics as in the prior two videos in order to clarify and make sure that there were no misunderstandings in terms of what was intended, because as the point I've made so far is that the Doppler and aberration expressions are in fact what special relativity is all about. The kinematic part, which was emphasized by Minkowski's reformulation, doesn't exist. It's a fabrication. And all the things that occur within the kinematic part of the 1905 paper can be explained with respect to how electromagnetic radiation is used to either measure or accelerate particles. With that, let's get to the visual materials I prepared, since they take up the bulk of this particular video, as do my explanations and discussion as I present those visual materials. This series of slides is both a summary and a restatement of things that have been discussed in the prior videos discussing Einstein's special relativity. In fact, all of the effects that Einstein discussed in his famous 1905 paper can be related to things that appeared in his electrodynamics. He had confused the effect of electrodynamic radiation pressure on objects with the actual movement of the objects themselves. He was just looking at the wrong part of the equation. So what we have is a series of scenarios that are going to be used because they're somewhat familiar to people. We're going to talk about the radiation pressure model and later the aberration model. In all instances, we're talking about things moving at a speed in Earth's orbit, either an object on Earth or something like a solar sail, which is launched from Earth orbit and therefore continues onward with the Earth orbital speed, plus a new radial velocity component being added by the pressure of the solar radiation moving radially outward from the sun, crossing the Earth's orbit and providing a force that accelerates an object then radially outward. You could look at this as a spiral type of orbit that would occur. The velocity of the Earth is 30 kilometers a second in orbit, and in this case, phi that is described in this model is 90 degrees because the Earth is moving perpendicular to the flux from the sun. For the radial motion, of course, phi then, in terms of the radial pressure, would be 0. For 90 degrees, you can see the cosine phi is equal to 0, and so you're left with just a simple dynamic term here, and we'll explain that a little bit later. And for radial motion, on the other hand, phi is equal to 0 and cosine phi is equal to 1, and so you're left with a more complex expression here. And we're going to be looking at these in what's called a small beta approximation, where beta is the velocity of the object over the speed of light. For the Earth's orbit, that's 0.0001. You very seldom get much larger values than that, except under very exotic circumstances or in particle accelerators. Also, this value of beta is always associated with the actual velocity of an object relative to the flux propagation direction. So what we're going to start with here is a description of the radiation pressure model. These are just a repeat of what was on the prior slide. You have dynamic factors associated with the motion itself. I call this the flux intercept factor, which is just one term of this without the square on it. And that relates to the fact that you're intercepting more radiation when you're moving at some angle relative to the flux direction. You could liken it to a light rain. And when you get in a car and you're driving and you pick up speed, the amount of rain hitting the windshield increases. And that's what I call the intercept factor. You're intercepting more flux. If you're moving, you can't do it with rain, of course, as an analogy. But with flux, you can be moving in any direction relative to the flux, and sometimes you have more or less. In effect, if you can move fast enough, you can outrun the flux, and so you'd wind up with zero flux intercept if you're moving close to the speed of light. And of course, you have here the Doppler expression, which is that expression without the square. And this is what Einstein identified uniquely and for the first time in his 1905 paper, which is the relativistic Doppler equation. But this does not contain, as stated, the aberration, and we'll talk about that. Just to refresh people, the way Einstein derived his equations, he did it with respect to rays of light. Here's the incident radiation. It's moving in a particular direction. It's a plane wave, and which means that it's very, very well defined in moving in a particular direction with a plane wave front. That's not really critical to this, but this is a normal to that wave front. It consists of a ray, and Einstein viewed radiation propagation as rays of light propagating in a particular direction. This is the observer's direction relative to that incident flux, and the direction of incident flux can be related to angle phi that we discussed before, which Einstein used in his derivation, and another angle theta, which is a supplement. We will show a series of these other angles because to make a measurement, you must be looking at the direction of the source of the flux. And if you're not looking at the direction of the source of the flux, then you're not really measuring it, which is true of a telescope, and as you'll see, it isn't necessarily true with respect to an object that is just moving in orbit like a solar sail. So these are a series of angles that are well defined via trigonometry. And what you have then is, because once the incident flux is intercepted by an object, a physical object of some sort, whether it be a telescope or just a solar sail, what you have is a deviation in the path of that radiation. And that's the deviation is measured relative to the incident angle. And so you have an apparent incident angle. So this is looking at it from the perspective of what happens for an object, whether it be a telescope or just a solar sail or anything. Incident radiation comes and impacts the object. The object is defined with a normal to the surface at any given point. This is the angle phi that we saw before, and this is a supplemental angle. If you're in this plane and you're looking at the source of the radiation, you're looking at angle theta relative to the direction of motion of the object itself. And you also then have relative to the normal, which is another way of looking at the angles associated with incident to reflected radiation. You have an angle phi, and because of the aberration effect, there's a deviation in the radiation once it interacts with the object, and the deviation is in the direction of motion, and it can be given by this simple expression. So what we have is looking at this. We've got either a solar sail or a telescope, and it's moving at a particular velocity v at some direction. It has two components. It has a radially outward direction, and it has a tangential or a direction across the flux. And this is the flux from the sun, and this is an object that's moving through that flux. So back to the radiation model. What we're going to do, the static dynamic model is broken into two pieces. This static portion is the only portion that's used. And here what we have is the radiation at some distance from the sun, at a distance r from the sun, is basically normalized by, we'll pick Earth's orbit. At Earth's orbit, we can measure the flux. We know what the radius of the Earth's orbit is. Therefore, we can find from the static model a pressure at any range r from the sun, whether it be in closer to the sun or further out, relative to the value at the Earth's orbit. And here you have your dynamic components in. One is associated with the Doppler effect, and the other is associated with what I call the interactive effect. So if we break this motion into two pieces, we have radial motion only, and we've got the small beta approximation. And for radial motion, we have phi equals to 0, and so that this whole dynamic portion reduces to this term. Therefore, the radiation pressure is reduced by a small quantity relative to the static model. We only use the static model. At this point, we ignore all these dynamic components. They're not taken into consideration. Therefore, we are overestimating the solar radiation pressure on an object by this amount. Again, remember, beta here is related to the actual speed of the object relative to the direction of motion of the flux. So the second part of this scenario we can look at, then we can say, okay, what can we say about the motion of the Earth or an object in motion at Earth's orbit, and the fact that the angle phi now that's indicated in this expression is at 90 degrees. And so all of the motion is transverse to the flux. Again, this is still the same beta that was used before. These are not recognized. None of these are recognized, nor is the transverse force recognized. So if we look at the transverse Doppler, what we have here is motion at phi equals 90 degrees relative to the flux direction. That reduces this the intercept factor to 1 because we're not intercepting any additional or less radiation by moving across the flux. And in a small beta approximation, what we wind up with for this dynamic term is this, but it's wrong. And it's wrong because we're using the angle phi. And before we mentioned, you have to be looking at the radiation, at the source of the radiation, where it's coming from, in order to be able to properly use this particular equation, because that's not where we're making a measurement. So here are the expressions again that we're going to be working with. You've got the relativistic Doppler, and you've got the relativistic aberration. What this says is if an object is moving through the flux at some angle phi, and it has a beta or speed related to a value beta, then the reflected rays are deviated or appear to come from another angle phi prime, and the deviation itself is then the difference between the phi and phi prime. So what we have to do is take a look at the relativistic Doppler as measured by whatever apparatus is, whether it be via a radiation pressure and noting deviations in movement of an object, or whether it's by looking at a telescope. What we have then is a relationship between the angle phi prime here and phi, and what we find is that using these trigonometric relationships, we can relate cosine phi pi, which is the cosine phi, which is the aberrated direction, to an aberration in the look angle, I call it, which is when we're looking back towards the source. So making the substitutions into this equation, the relativistic Doppler, accounting for the fact we're looking at another direction, and this is what we measure, we can see that the frequency then is changed. The Doppler frequency that is measured is now given by a new term that is in some ways the inverse of this term. This is what we actually measure because we're looking at the radiation and intercepting it. So when we put those values in and use a small beta approximation, again, as we did before, what we find is that we have a new frequency component, frequency prime, that we would measure or would be experienced, given by this expression. Note that we don't currently recognize that there is a transverse component associated with the velocity, which has its source in the aberration. So now we no longer just have a single value. What we have is now a new pressure that did not exist before in terms of our analytical models that's given by this term. There is no transverse pressure unless you consider the existence of the aberration effect. Once you do that, we find that we have a new unknown transverse pressure on the object, which can translate into a force on the object, moving it in a transverse direction. Notice that both in this case, the dynamic component, and in the prior case of the radial Doppler, they're both negative, which means that they are both effects are acting to slow the object relative to what we would define that motion to be using just a static model. In other words, from the transverse perspective, this is slowing the object down so that it doesn't pick up speed and accelerate out of bounds. So that's the effect of both of the dynamics, is to basically have factors that not only change the value of the static model, they are pointed in a direction to provide forces that are slowing the object down both in orbit and in radial motion. So now that's the first scenario. We have forces that are tending to slow the object down and that reduce the value of the forces on the object because radiation pressure is reduced by the dynamic effects. Here we have the same scenario, but we have a telescope on Earth that is looking towards the sun. And so this is what the equation is that measures it, because we're now looking at an angle theta prime to determine what our new frequency is. Notice that when new prime equals new, in other words, no Doppler shift, we have an angle at which that occurs. That says that if we're looking at the sun at an angle directly towards the center of the sun, at a small deviation away from that angle, you at an angle given by minus beta over 2, we have no Doppler shift. In other words, there is no impact by looking at that point from either the aberration or the motion of the telescope perpendicular to the flux direction. But if we, and we'll show this in the next slides, if we look at an angle beta away from the center along the solar equator, there is no Doppler shift at that particular point. However, for any angle in either direction along the equator relative to that offset angle, the frequency experiences a small redshift. In other words, the frequency becomes smaller. It means that the wavelength becomes longer. This is all called a redshift. What are we talking about? If we're looking at the sun, we're on Earth, what we experience is an angle theta prime because we're looking towards the sun, which is back towards the source of the radiation. And if we use, and this is where an instantaneous pixel might be looking at across the equator of the sun, and this is called scanning from the one limb of the sun to the other limb of the sun. When we look at an angle of minus beta over 2, we have no Doppler shift. But when we look at the whole scan across the sun, what we see is we have a peak, which is the fact that we have no Doppler shift, and then we have a Doppler shift that's decreased, it's redshifted, and so we wind up with an effective change in the
relationship nu prime to nu, and it decreases. This has been seen and measured but never explained. It's because the explanations never included an analysis and a model of what the sensor is measuring relative to the Doppler and aberration equation. The models have been incomplete, and so they've had no explanations. They've tried a lot of very strange and exotic explanations, and they haven't come down to it. In particular, this is called there's a strong ionized iron radiation line that's been measured, and this anomalous redshift that they see when they look across the sun has been called the redshift anomaly or crisis or some other name. The iron frequency redshift crisis or anomaly. So now this is a possible explanation for what's going on. But you have, if you're making a measurement that includes either directions or frequency, you must include the aberration effect, or you're not going to be able to properly account for what you're looking at.
So in the next video, what we'll do is we'll expand how we would apply our knowledge of the Doppler and aberration to explain other things that we've seen or measured or might measure in the future when we get out of the realm of operating in the small beta approximation. And with that, I'm going to wrap this up. I'm Luther Name. Leave a comment or subscribe, and stay tuned for the next video in this series, video 16.